families of optimal gates. Before I dive in, I first want to clarify some terminology. So what are families of gates, what is actually a gate, and what does it mean for a legged system to be optimal. And in this talk I will consider a really simple legged system, the compass gate walker. And in the beginning, like, what is a gate? A gate here is a periodic motion that is represented by this periodicity map, the P, including the collision. Then the optimization part is here we have an actuator at the hip, so we want to use a minimal energy consumption to get these periodic motions. And then at the same time we want to have a certain desired forward speed for this robot. And we want to operate this robot at different speeds, and this kind of leads to our family of gates. So we can generate a family of gates, and now I want to dive into the math actually. So how do we solve this problem? So we first formulate this as an optimization problem where we have our objective function, our costs, and our constraints, and there are typically two methods to solve this problem. The one that everyone is using is the direct method, and then there's also the indirect method. And which should we take here, and what is the difference actually? I will explain it with this cartoon. So the direct method is taking the problem and discretizing the problem first, so we can put it in a computer and then solve a nonlinear program. That's the direct method, that's what everyone is doing. And the indirect method is first doing the optimization part, so using the first order optimality, and then we discretize our problem, our optimality conditions, and then we arrive at our solution. In more mathematical terms, and here we use signal shooting for the discretization part, the direct method approximates the function space U here. So the input space is infinite dimensional. To put it in a computer, we have to discretize it, something like this. And then we get an optimization problem, and actually a nonlinear program that we can solve numerically. And in the indirect method, actually we start with the optimization part. So we use this infinite dimensional function space and do calculus of variations and get this Hamiltonian function. And here we have our cost U squared, and the P is kind of a continuous Lagrange multiplier, also called costate. And the nice thing here is that our optimal actuation actually is a function of P and our state X. And then at the end we just have to solve a quite ugly boundary value problem, but this again can be discretized and then solved numerically. And both approaches can actually be written into an implicit function. So the direct method, we can use the Karush-Kuhn-Tucker conditions, optimality conditions, and write this in an implicit function where we have our decision variable, period time, initial state, and all our input parameters. And for the indirect method, we can do something similar. So why is everyone using the direct method? Like for the indirect method, as you can see, it's quicker in its evaluation because we have less parameters, less decision variables. But it's one drawback of the indirect method is that we need a good initial guess. So the local convergence or the global convergence actually is worse than the direct method. That's why most people relate to the direct method. But what if we have a good initial guess, actually a starting point here, like this solution, then we can actually locally connect this to higher speeds using so-called numerical continuation methods. And that's how we actually generate our library or family of optimal gates. And then going back to this example, so we have an initial gate at slow speed, and then we use continuation methods to trace the solution for higher speeds, and so on. And this is all using the indirect method. The nice thing is it's using a real high accuracy computing all of these gates because we don't have to parameterize the input space, and using signal shooting we have these adaptive step sizes in the integrator. And the nice thing here is, like, using MATLAB I generated 100 optimal gates in roughly 2 seconds. So it's really quick fix. An open question here is you can see it's barely moving. Actually, can we also go to a gate with 0 speed? The nice thing here is this would be standing still, would be a trivial gate. We don't need any actuation. We can actually compute this analytically. The issue here is it's a singularity, so it's kind of difficult to branch off the singularity and then generate this. So this is an open research question still. And with this, I want to thank my collaborators and funding sources. And I want to end my talk actually with a haiku. The indirect way for library of gates, this path is quicker. Thanks.
Based on the animation, I'm guessing for the higher speeds you're finding the solution is just short period. Okay,
yeah, the period time is decreasing. Yeah.
You're not finding the long period gate when the swing blade goes down and then comes back.
Yeah, that's a good observation actually. For lower speeds, you can see how the lag is impacting from above, and then at higher speeds, it's impacting from below. That's true. Yeah.
For this curve right here, for say a more complicated system where you have constraints and all that jazz, does the continuation, the numerical continuation method, would it be possible that there's like a discontinuity in this curve in such circumstances?
That's a good question. So here I'm only using equality constraints. So incorporating inequality constraints usually causes kinks when you do continuation. One way is to use it as a soft penalty in the objective function to account for this, but this is also just open research to me. So but it's challenging, especially with the indirect method. Like inequality constraints is not trivial to deal with.
Yeah, I was just curious, like how complex can your model be before this indirect method not? I think it's hard to apply the indirect method.
Well, it always goes down to a good initial guess like this one, or actually using other passive gates like walking down a slope where you also don't need any actuation. So these can be good starting points to use the indirect method. And computationally, they're actually quicker than using the direct method, because for the direct method, you introduce another overhead of variables, so it's lower dimensional.
The dimensions of your problem?
It's lower dimensional than the direct method. So at some point, you still have an issue. It's growing, but it's the same thing with the direct method. But yeah, you're still, also with the increase of actuators, you still don't need all of these guys. So P has the same dimension of X. Yeah.
So do you have any intuition why people are not using this more like complex?
Why they don't use it?
Yeah.
It's because of the convergence. So the indirect method, like getting a good guess for P naught is really difficult.
Yes.
Yeah.
Start to play with like arbitrary costs or things like that. Do you necessarily have, are all the optimal solutions necessarily on a continuous path, or can you always find all of them starting from one optimal solution? Or can there be jumps that you can't actually go from one optimal solution to another?
Well, the continuation itself relies on local connectedness.
Yeah, so are all solutions locally connected? Like, have you always found a path that?
Yeah, that's difficult to say beforehand. So it really depends on the problem. And it's also, I'm only talking about local optimality. So the indirect and direct methods only find local optima.
Okay.
So there might exist different local optima at the same average speed, and then, yeah, like finding the right one that has the lower cost is difficult. Like switching is not trivial. Yeah. Okay. Thank you.